In this lecture, we will be looking at the direct comparison test for convergence for infinite series. Roughly speaking, this test says if you are given a series of positive terms and you find another series of positive terms that's bigger and also converges, that forces our given series of the a sub n's to also converge. To go through the details, here's our given series, the sum of the a sub n's. The a sub n's are non-negative. And we have another convergent series of u sub n's, and I'm using u to think of upper. So u is above a sub n. It's greater than or equal to a sub n. To each of them, eventually. So once you hit some capital N, from there on, all of the a sub n's are less than or equal to the u sub n's. This just means that it eventually has to be the case, starting at capital N and then always thereafter. Because the sum of the u sub n's is convergent, and the u sub n's are bigger than the a sub n's, the sum of the a sub n's is a smaller series. Both are non-negative. All the terms are greater than or equal to 0. So we find, if we can find a bigger finite series, if it's bigger and finite, our given series a sub n also has to be finite. And so the key way to think of this is that the sum of the a sub n's is dominated by the sum of the u sub n's. This inequality here really demonstrates that. So again, all of our terms, the a sub n and u sub n, are non-negative. So we know our a sub n's, that's greater than or equal to 0, the sum of the a sub n's. But starting at capital N, the u sub n's are always bigger. So that sum of the a sub n's is smaller than the sum of u sub n's, but we said the series of the u sub n's is finite. So if this is finite, the sum of the a sub n's also has to be finite. This can be seen nicely if we think about, suppose this is what our a sub n's look like. So here's our number line, and we have time 1, 2, 3, 4, 5, 6, so on and so forth. And let's depict our a sub n's. Think of it as adding up areas. So think of summing up these orange areas, and that makes up our series of a sub n's. So think of this as, if we throw a y-axis here, think of that as our a1, a2, and we'll draw it here, a3, a4, so on and so forth. What we're saying now is we find another series that's bigger. And these will be what we called our u's. So our u sub 1, u sub 2, u3, u4, u5. And coming back to our area issue, think of the sum as n goes from 1 to infinity of a sub n being that orange shaded area. Well, if we have this blue area being the sum of our u sub n's, and again, u sub n, we're choosing that for upper. So each term each U sub n is above each A sub n. And again, this has to start at some index, and here we're just depicting the case where it starts right off the bat. But as long as it starts somewhere and then always holds, this result is valid. And the idea is, if this blue area is finite, but it's bigger than the orange area, it forces that orange area to be finite. And so again, we're dominating the series. This is the series you can think of as being given, and we're finding a larger convergent series that dominates it, forcing our given series of A sub n to also be convergent. Let's look at a couple examples. Here we have an example, sum n goes from 1 to infinity of sine squared of n over 2 to the n. Well, we know, first of all, that sine of anything is between -1 and 1. But of course, that means if you square it, you get something between 0 and 1. Well, that means, looking here at our summand, we have sine squared of n being between 0 and 1, and then we can divide every term here by 2 to the n and maintain the inequalities, and we get 0 less than or equal to sine squared of n over 2 to the n less than or equal to 1 over 2 to the n. And if we were to think of this, if we were to color code this as we had before, you want to think of this sine squared n as over 2 to the n as the orange depiction we had before, and our 1 over 2 to the n as the blue depiction before. So you can think of these blue areas as your 1 over 2 to the n terms, and the orange areas as the sine squared n over 2 to the n. But what's nice is that we know how to handle the sum n going from 1 to infinity of 1 over 2 to the n. That is the sum n going from 1 to infinity of 1/2 to the n, which we recognize as a geometric series with a ratio term r equals 1/2. And recall, for a geometric series, the convergence criteria is that r in absolute value is less than 1/2, which we have here. And so this is a convergent geometric series. And because of this inequality, and notice this works for all n bigger than or equal to 1, by direct comparison, our given series must also converge. So therefore, the sum n going from 1 to infinity of sine squared n over n converges by direct comparison. And we also have to recognize we do not know what it converges to. We only know that it does in fact converge. But you can use this to conclude that it does converge, and then you can use software to estimate what it converges to. So it's important to recognize that, as illustrated by this example, the direct comparison test just gives you yay or nay. Your series either converges or it doesn't. In this case, we were able to conclude that it does converge because we found a larger convergent series. And it's also important to remember, for this to work, you have to guess right. We had to guess that this, in fact, was a convergent series and find a larger convergent series. If it, in fact, was the divergent series, you wouldn't find a larger convergent series because such a series would not exist. Let's look at another example. The sum going from n going from 1 to infinity of 1 plus cosine of n over n squared. Now when we look at this and kind of feel this out, we say, okay, the numerator, you have 1, and then you're adding something to it that bounces back and forth between, in the interval, -1 to 1. But the denominator is an n squared. And we should think p-series. So the sum of a constant over n squared we know will converge. So we can guess that this is going to converge by direct comparison, and we can take a similar approach. We know that cosine of n lives between -1 and 1. If we then add 1 to each term, we get 0 less than or equal to 1 plus cosine of n less than or equal to 2. And then we note that for n 1 or greater, we can always divide by n squared, which is positive. So we can divide everything by n squared and maintain our inequalities. And then we have 1 plus cosine of n over n squared less than or equal to 2 over n squared. And we now see we have found terms that are larger that we can understand their behavior if we sum them up. So the sum, n going from 1 to infinity, of 2 over n squared, again, we know this is a convergent p-series, where p is equal to 2, and remember the criteria is that it be bigger than 1. And if you really want to be specific, technically we should probably say this is 2 times the sum, n going from 1 to infinity of 1 over n squared. But because we have found a larger convergent p-series, the sum of our 1 plus cosine n over n squared term also has to be finite. So this means the sum, n going from 1 to infinity, of 1 plus cosine of n over n squared, which is less than or equal to the sum n goes from 1 to infinity of 2 over n squared. Right? That's less than infinity. This converges by direct comparison. So again, we see we only can conclude that our given series does in fact converge. We don't know what it converges to. And also, we have to remember that in order to successfully use the direct comparison test, we do have to guess right. So there's a lot of value in being able to look at the series and think about it. And when we looked at this, we said, this looks an awful lot like 1 over n squared, or 1 plus a little bit of noise over n squared. And that led us to use the p-series approach. So again, this is a very useful tool. It's also a nice intuitive tool because in terms of convergence tests, this concept is kind of a natural one. You have a sum of positive terms, you find a sum of bigger positive terms, and that sum is finite. Well, that makes the smaller sum also finite. So that's the gist of the direct comparison test for convergence.